All right, so what does this linearization tell us? If a function is concave down on an interval, which we talked about concavity in the last block, the tangent line to the curve will be above the curve, and therefore the tangent line approximation, or the linearization, will be an overestimate for the actual value. All right, this makes perfect sense if you think about it. If the curve is concave down, the tangent line to the curve would look something like this. And if we're going to use the line as an approximation to the curve, it's going to be above the curve. Therefore, we would say it's an overestimate of the actual value of the curve. If the curve is concave up on an interval, then of course when we draw the tangent line to the curve is going to be below the curve. Therefore, the tangent line approximation, or the linearization, or the line itself, will be an underestimate to the actual value of the curve. So our goal here is actually we're going to use the value of the line to approximate the value of the curve when we don't have a lot of information about the curve, or if we don't necessarily have even the curve. We're going to use that linearization. But we should also note that if we have the concavity of the curve, we know whether it's going to be an underestimate or an overestimate. Here's an example of how we would use this. Now, this is not necessarily in your lecture guide, but this is something that is good to use for us for approximating the curve. So if I told you, you know that the value of some curve, say a profit curve or a revenue curve or a cost curve, was saying that we know that G at 20 equals 5. Of course, I don't have units here, but I know these values. And if I knew that the derivative, or the rate of change of the curve at that same point at x equals 20 is equal to 1.4. So that's the only information we're given about our curves. We're only given the value of the function and the value of the derivative at that particular point. It says, well, use this information to approximate the value of the function at 23 and the value of the function at 18. I don't have any information about this curve other than this given information. I don't have a function, I don't have a graph. However, we could use linear approximation here because all I have is enough information for a linear approximation. I have a point on the curve, which is the point 25, so the point 20, 5, and I know the value of the slope at 20 at that point of tangency. I know the slope of the curve is equal to 1.4. So I could put this into the linearization. I could say, well, the value of the function is really close to the value of this line near 20, and 23 and 18 are relatively close to 20. Now, if I were asking for information about G at 50 or G at 100, this linear approximation wouldn't be very good because those aren't very close to 20. But because I have some information here that's pretty close to 20, I could use the linearization to approximate the value of the function. So what I'm going to do is I'm going to use this for the value of the y value of the function, which is 5. The derivative of the function, which I know at 20 was equal to 1.4, and the x coordinate that I'm talking about here is a, which is at 20. So I can find the linearization by just from the information they gave me. They gave me a point on the curve, which I can put in. Here's the x coordinate, here's the y coordinate, and I can put in the value of the derivative at that point, which is 1.4. I now have a linear approximation to the value of the curve. So now I have a formula that I can use to approximate these other two values. So using this tangent line approximation, G at 23 is going to be really close to L at 23. That's what this linear approximation formula says. That means I'm going to put 23 into the formula I just found for x. And when I do, I get 5 plus 1.4 times 23 minus 20, which when I do the math is equal to 9.2. 9.2 is a really good approximation to the value of this function at 23. Again, I can do the same thing at 18 using the same equation. I'm going to put here the value of All right, so I had a typo there that I had to fix. So now we'd say that the value of the function at 18 is really close to the value of the linearization at 18, which I put in 18 for x to get 2.2. So this is a way that we can, if we don't know a lot of information about a function, but we do know the derivative and the point of tangency, we can get a good approximation to the value of the curve at that particular point. The second concept that we're going to talk about today is elasticity. Now, elasticity of demand you might have heard of in your business courses. We know that demand functions are decreasing, so when the price increases, the quantity demanded usually goes down. But what about the revenue, which is the price times the quantity? When the price increases, will the revenue always go down because the demand is dropping so much? Or will the revenue increase because the demand didn't drop very much? This is the concept of elasticity of demand. Here's the definition. Let's go through. Elasticity of demand is a measure of how demand reacts to the changes in your price in your company. It is normalized. That means the particular prices and quantities don't matter that much, and everything is treated as a percentage of change. The formula for elasticity of demand involves a derivative, which is why we discuss it in business calc. Before I go on to the next slide, I do want to point out this bottom picture down here. When we're in class, and I wish I could show you this in a video form, but when I'm in class, I actually often use a rubber band to understand this concept of elasticity, and I'll talk about that in just a second. So here's my elasticity of demand. Given a demand function that gives Q in terms of P, the elasticity of demand is defined by the absolute value of P over Q times the derivative of Q with respect to P. So I want to just look at this formula for a few minutes. You might have already seen it in other business courses, but let's look at it as far as the math is concerned here. In order to find a elasticity of demand, we're going to need a couple of things. We're going to need the demand price, that's P. We're going to need the demand quantity, which is Q. And we're going to need the derivative of the demand quantity in terms of price. So in order to use this formula, we have to have Q in terms of P, and we have to be able to find the derivative there. So note that since the demand is a decreasing function of P, the derivative is always going to be negative. So this derivative is always going to be negative. So we usually take the absolute value of E. So it will now be always positive, and we could talk about it in positive terms. Now, in the lecture guide, I know Mrs. Taylor left it as a negative value, and she started looking at it as a negative value, but most places in business, when we talk about elasticity of demand, we think of it as, we refer to it as a positive number, but then analyze it using its positive quantity here. And that is this. Given the demand function that gives Q in terms of P, so that again is going to be essential. We're going to have the demand quantity in terms of P, so we should be able to have Q equaling P's. The elasticity of demand formula is given here. If our result, when we put this on the calculator or in Excel, we get E is less than 1, that is a fraction between 0 and 1, we will say that the demand is called inelastic. In this case, raising prices increases revenue. So we say a E of less than 1, a fraction between 0 and 1, we say the demand is inelastic, and raising prices raises revenue. This is a good thing. We can raise our prices a little bit, and our revenue will still increase. If that elasticity is greater than 1, we say the demand is elastic. And if you think of this as putting a rubber band at the tip of each one of these arrows, just like I would at the tip of each of these, tip of a finger or a tip of these arrows. Notice with inelastic, as one rises, the other rises. If I put a elastic band around this one, it'll pretty much stay the same. But if I put an elastic rubber band around this and this, it will tug away from each other. Notice raising prices will decrease revenue. So the two things are going to be elastic, or they're going to compete with one another. If that E value, elasticity of demand, is 1, we say the demand is unitary. E equals 1 is going to happen at critical points of the revenue function, and this is where the revenue function is going to be the highest. Here's our interpretation of elasticity of demand. If the price increases by 1%, the demand will decrease by E%. However, when I say E, notice I am not going to manipulate E to change it to a percent. I'm just going to give E whatever E is and put a percent symbol on it. So if I raise my prices by 1% and E was less than 1, that means I could increase prices by 1% and the demand will only decrease by a number less than 1%. Therefore, I'm going to get more revenue than the decrease will affect my function. However, if my E is greater than 1, then if I increase my prices by 1%, the demand will increase by a number more than 1%. Excuse me, my demand will decrease by a number more than 1% because this will be greater than 1. That means the 1% is going to be less than the amount of decrease, so it's actually going to hurt my company, so my revenue will drop. And E is equal to 1, which will be the same. Let's say the price increases by 1%, the demand will decrease also by 1%. So it really won't hurt or help my revenue. So the price elasticity of demand is always denoted by E. It is the percent of change in the demand as the price increases by 1%. So we say that demand is inelastic when E is between 0 and 1. We say the demand is elastic when E is less than 1. Whoop, that's not true. That is greater than 1. There you go. I'm sorry about that. I had another typo I had to fix. We say the demand is elastic when E is greater than 1. And elasticity is called unit elastic or unitary when E is equal to 1. When elasticity is a unit elastic, we will see the highest revenue there. That's where we're reaching the critical points of the revenue. So let's do an example without actually doing any numbers. Let me just give you some numbers here and then see what it says. For example, if I said to you, a price elasticity of demand is the absolute value of negative 0.4. In other words, 0.4 is my E. It means that the price increase of 1% will decrease my demand by 4%. Excuse me, 0.4%. So in this case, I should raise my prices 1% because even though less people are going to purchase my product, it will increase our revenue overall because the decrease in the items sold is smaller than the price of an increase. So if we price increase by 1%, we're only decreasing our demand by 0.4%. So yeah, I'll increase my price. It's not going to hurt my revenue very much. But what about something like this? For example, a price elasticity of demand of negative 1.2, or the absolute value, which means that the price increase of 1% will decrease my demand by 1.2%. So increasing my price 1%, but my demand is now decreasing by more than 1%. So that 1% increase in price is decreasing my demand by more percentages than I want. So in this case, we should not raise our price by 1% because increasing the price by 1% will decrease the number sold more than 1%, and therefore our revenue would decrease. This is